Good morning, good afternoon, or good evening, depending on where everybody is. Sorry, I'm a little bit late in getting started. A minor technical itch before things got started. But thank you for joining me this Wednesday morning. My name's Craig Williams. I'm coming from the AMETEK Solidstate Controls Service and Training Center in Stafford, Texas. And if you don't mind, if everybody can, or some people can put in the chat bar whether you can hear me or not, that would be greatly appreciated, because there's no point in me carrying on speaking if you can't hear me. So today's webinar is called How Does an Inverter Work? And basically we're going to go over the very basics of how an inverter works. In fact, let me bring up the next slide. And the two designs that we use. Thank you very much, everybody, saying that you can hear me. I appreciate that. And also, if you just want to get used to the webinar jam interface, on the right-hand side of your screen, you should have a chat bar, and you can answer questions as we go through the webinar, ask questions, sorry. And what I'll usually do is leave them until the end of the webinar to start answering any of the questions that you have asked. So once again, my name is Craig Williams. I'm the Senior Technical Manager here at AMETEK Solidstate Controls in Stafford, Texas, just south of Houston. I have 20 years in the industrial UPS industry for my sins. I used to work in the North Sea off the coast of Scotland, as you can probably tell from my accent. I've worked with all of the major UPS and charger manufacturers over those years, both in North America and in Europe. So I'd like to say I know a little bit about UPSs and chargers. There will be a lag of around 30 seconds between when I speak and when somebody asks a question. Basically, Webinar Jam has to process this webinar and send it out to Android systems, to iPhones, and to Windows-based systems. So there is some processing that gets done during that time. So from the moment I speak to the moment you hear it is going to be about 30 seconds. The platform we use is called Webinar Jam, and it does have a panic button. So if something goes wrong on my end and I see that something has broken, I can press the panic button, and what will happen is everybody will be kicked out of this room. Webinar Jam will automatically start a new room, and everybody will be invited back into that room, and we will take over from where we left off. Okay. A common question is, will the webinar be recorded? Yes, the webinar is recorded. And if you've signed up for the webinar, which obviously you have if you're watching this just now, then you will receive a link after the webinar to, you can go back and watch the webinar again through Webinar Jam. The issue with that one is it gets displayed as if it's a new webinar. So you can't fast forward it, you can't rewind it. So you have to watch the whole thing from start to finish again. But what our fantastic marketing department do is they will then take that video and convert it to an MP4 and then upload it to the AMETEK Solidstate Controls YouTube channel. And it will be uploaded probably tomorrow, and it will be available for you to watch, and you can fast forward, rewind, bookmark it, do whatever you want to it after that. And as usual, the webinar should last around an hour. Once again, it depends how much I speak, and it depends how many questions we get from everybody. Okay, so that's a good overview of Webinar Jam and the webinar today. So our learning outcomes today are going to be understand basic inverter design, understand the two AMETEK SCI designs of inverter bridge that we use today, discuss the components used in that design, and then explain the benefits of each design. So hopefully you'll get something out of this today. So the first question is simple. What is an inverter? Obviously, it's a commonly asked question. What does it do? Well, it's quite simple. An inverter converts DC to AC. It's as simple as that. And there's a block diagram for it on the screen. On the left-hand side here, you have DC going in this way here on the left-hand side, and on the right-hand side, you have AC coming out. Now, depending on the design of the UPS, it can be 120, 208, 240, 480, or even 600 volts, depending on where you are in the world, and it can be 50 or 60 hertz. So you can get a wide range of AC outputs from an inverter. But in its most simple form, an inverter converts DC back into AC. Okay. So here is a diagram to show you how a basic inverter works. And electricity is, let's face it, it's a bit of a pain in the neck because you can't see it, you can't smell it, you can't feel it. Well, if you're feeling it, you're doing something wrong. But, it's very difficult sometimes for people to get concepts in their heads. So I like to do things that have physical action. So in this diagram here, the M is a DC motor, okay? And on the left-hand side, we have our DC going in. So let's pretend that this is actually a battery, okay? And for industrial use, it's usually 135 volts or 60 cells, okay? Now, that battery is always going to be there, ready to supply power when necessary. And then on the right-hand side, we have an H-bridge formation, and we have 4 switches. We have S1, S2, S3, and S4. And you can see at this moment in time that S1 is closed and S4 is closed. S3 is open and S2 is open, okay? And if we follow the power from the battery, so here's the positive here. So if we follow the power through here, S1 is closed, so power will be allowed to go down this way. S3 is open, so power will not go through this way. So that makes this side of this DC motor positive. Now we have to have a complete circuit for any electronic circuit. So the other side of the motor comes out and returns through switch 4 back to our negative of the battery, okay? And that makes this side of the motor negative. Now in any DC motor, basically what you're setting up is an electromagnetic field. So let's just say that makes this pole north and it makes this pole south. And that makes the motor turn in a clockwise direction for this example. So hopefully you follow me. And that basically allows the motor to turn in the clockwise direction. And the motor will keep on turning in the clockwise direction until the switches are opened. So that would be, we're still basically supplying DC at this point. But to create AC, what we need to be able to do is make the motor spin in the other direction, okay? And to do that, all we do is we open S1 and S4, and then we close S2 and S3. So once again, we've got our positive here. So let's follow the power this way. Now S1 is open. We can't go through that way. So therefore, that is blocked. But S3 is now closed, and that makes the right-hand side of the motor positive. And the left-hand side is now negative because it is connected directly to the negative through S2. Okay, so that now makes this side of the motor north and this side of the motor south. And that allows the motor to spin in the reverse direction. In this case, it would be counterclockwise. So you can see there, just by the simple operation of 4 switches in pairs together, you can have a motor spin in one direction and then in the other. And if you replace that motor with a transformer, basically what you're creating is an AC signal. It would be a square wave, basically, into that transformer, which can be considered to be AC. So that is the basics of how nearly all inverters work. They use switches to be able to switch the power from the DC and convert it into AC. Okay, so hopefully everybody is following along. Now, what you don't want to do is you don't want to close S1 and S2 together, because as you can see from this diagram here, that creates a direct short across the positive and the negative of the battery. And that's how you let the magic smoke out of most things. It's a bad day if you close two transistors at the same time. Basically, it will usually cause destruction of the inverter bridge. So most manufacturers have their design so that will never happen. Okay. So the devices that we use, what we've shown before is physical switches. And actually, if we go back in this case here, you know, all we're doing is changing the direction of the motor. So you could actually have these as mechanical switches because it doesn't have to be done quickly. You can have switch S1 and S4 on, and then a few seconds later, if you wanted to, you could switch S2 and S3 on and make the motor spin the other direction. You don't need high-speed switching here, and using switches wouldn't be an issue except for the arcing across the contacts, which could cause an issue. But what we do in inverter technology is we use IGBTs, or insulated gate bipolar transistors. Okay, it's a bit of a mouthful. That's why we say IGBTs. And some people can get hung up on what an IGBT does because, you know, they figure it's got the word transistor in it. So they think, oh, okay, transistors are used in audio amplifiers and many other kinds of circuits where they are used in their linear range and you can do fancy things with them. For us, all we are using the IGBT for is a power switch. That's all it is. We send a signal to the gate, we turn it on, and then we remove the signal from the gate and we turn it off. It really is as simple as that. Don't get hung up on what an IGBT does. Okay, it is just a power switch that we can send a signal to switch it on, and and then remove the signal and switch it off. And then a lot of other people get confused with this diode that's inside most IGBT designs. That diode is called a freewheeling diode, and basically what happens is, you know, if you switch this IGBT on, you've got power flowing from the collector through the device itself to the emitter. And then when you switch the IGBT off, that power gets interrupted very quickly. And if any of you know what happens when you remove power very quickly from a circuit is a back EMF can be caused due to some inductance in the circuit. And what this diode does is it allows, because when you cut it off, the back EMF will have positive with respect to negative that way, and that will allow the power to dissipate through that diode and actually back into some capacitors that would be back here. But that's overcomplicating things. All you need to know is that an IGBT is just a switch that we can turn off, and we can remove the signal, and send a signal and turn on. Once again, it's electricity, so I like to try and figure out physical ways to show you how a device works. And this is basically its most simple form. The gate on the left-hand side is somebody's finger, okay? And the switch itself is a spring-loaded switch. And then we have our collector at the top here. So that's our collector. And then at the bottom, we have our emitter, okay? So let's say we have 12 volts at the top at the collector, okay? If we haven't pressed this switch, you can see the circuit hasn't been connected. We do have 12 volts at this point here, but it's not connected here. So we're going to have zero volts on the emitter, okay? The switch is open. And then all we do is when we send a signal to the gate, that finger presses that switch there and connects these 2 points together. And then that makes that 12 volts there, which can go out and supply other parts of the circuit as necessary. And then if you remove your finger from the switch, obviously it opens again because of the spring. Now, remember, this is an analogy. It's not actually how an IGBT works. And don't, I know it's silly, but don't put your fingers on electric circuits when you're out in the field. It's just a way to show you how it works. Okay, and here's another analogy that I like to use because it's got water or fluid in it. On the left-hand side, well, we have two solenoid controlled valves here. And on the left-hand side, we have gate off, and on the right-hand side, we have gate on. And you can see we've got our coil here. And if we've got the gate off, that means this coil is not energized. So therefore, you can see this plunger has sealed this opening. So the valve cannot pass fluid. It stops there. So the gate is off, therefore the transistor is off. But on the right-hand side, if we send a signal, we say gate on, then we energize the coil here. And that sends a magnetic field that pulls up the plunger, okay? It gets attracted to the armature, and therefore that allows the fluid to flow from a collector to the emitter. So hopefully those two analogies give you a better idea of how an IGBT works. But once again, you send a signal to it, it switches on, you remove the signal, and it switches off. It is as simple as that. It is a power switch. Okay. And this is what an IGBT looks like. Now, this is a power IGBT on the left-hand side. That's a single IGBT. It only has one IGBT in that package. And on this picture here, you can see down the bottom, there is actually two IGBTs in this package, and they share this terminal here. And it's designed in such a way that they can be very easily inserted into an inverter bridge. So that is the two main designs of power IGBTs. And I always like to show this picture because if you see an IGBT like this, then something's gone wrong. You have let the magic smoke out. This is what a damaged IGBT can look like. And the problem with IGBTs is they are very, very current sensitive. They are very sensitive to high current, and there is no fuse on this planet that can protect an IGBT from destroying itself from a high current situation. It has to be done electronically through the control circuits. So if there is a problem with the IGBTs or the control circuit and two IGBTs do switch on at the same time and cause a direct short, then this picture here shows you what it will probably look like after the fact. So try not to do that. So that's the basics of an inverter bridge and IGBTs taken care of. So this picture here is actually from our oldest and most common design of UPSs that are out there at this time. And this is for the Microfero SE UPS, or it's a system that has a CVT transformer in it. It's now, the model is now called the DSE, the Digital SE. Okay. So I'm going to try and explain this circuit. So once again, on the left-hand side, we have the DC input, which once again is usually from a battery. Now, yes, in most cases, you're going to have a battery charger out here as well, charging the batteries, but we'll just ignore that just now. We're getting our DC from the DC bus or the battery. Now, you can see here that the positive is connected to the center tap of this transformer. Okay, and then we have two switches down here. Now, once again, this is the basic version. This is without the IGBTs. It's just showing them as switches. And we'll move on from this and show you it with IGBTs in just a moment. But what I want to show you is how the power flows. Okay, so let me clear this. So the power flows from positive, and let's say S1 is closed. Oop. I put on my lines instead of my pencil. So S1 is closed, okay? So power will flow through the midpoint of the transformer, the center tap, down through this way. Remember, circuit has to get to the negative down here, okay? So that makes this positive on that side of the transformer with respect to that. So therefore, we get let's say this is a 0 volt line, okay? We get a negative going square wave. And once again, if it's a 60 cell system, 135 volts, that's going to be 135 volts in amplitude, okay? So that is for the negative portion of the sine wave. S1 is closed and S2 is open. And then all we do is we now open S1 and we will now close S2. Let's clear this. So let's close S2 and then open S1. And you can see the positive, the polarity of the battery doesn't change at the battery itself. The polarity gets changed through the center tap here. And now we go down this side of the transformer, down through S2, down to the negative. Now, that makes this part of the transformer more positive than this winding, which therefore gives us a positive square wave. Okay, the previous one that we did was a negative, and now we've got a positive. Now, if we switch those switches at 60 hertz, okay, basically what we've done is we've created a square wave at 60 hertz with the amplitude on each side of the battery, which is usually 135 volts DC. That's all we do. It is as simple as that for this style of inverter bridge. We are just switching S1 and S2 on and off at 60 hertz, and it creates a square wave on the primary of the transformer. Now, yes, this side of the transformer here looks very complex, and this is a CVT or a ferroresonant transformer, and I'm not going to go into what a ferroresonant transformer does today. All you need to know is when you put a square wave on the primary of this transformer, because of this capacitor here and the inductance in the transformer, the secondary magically creates a nice 60 hertz sine wave. Okay, it is as simple as that. So let's do the same circuit, but with IGBTs. And we flipped it up a little bit because it makes more sense when it's drawn like this. So once again, we have our battery connected out here. That's the positive and that's the negative. And we have our center tap of the transformer coming in here. So once again, let's switch Q1 on. This is an IGBT this time. So the power flows through here, down here. That part of the transformer becomes positive, and this side here is connected through the transistor directly to the negative side. So we have the negative portion going through that way, okay? And then once again, we're going to switch Q2 on this time. Positive, going down here. This part of the transformer is more positive. We go down here. And that negative is connected through the IGBT down this way here. And we get the positive part of the square wave. Okay? And it really is as simple as that. That is what our DSE and our SE inverter bridges do. They just create a square wave at the frequency desired, 60 hertz in North America and many other countries, and 50 hertz in Europe and Asia and other places. Okay. So this is a square wave that I got from the internet. So let's say that our battery voltage was 100 volts, just for ease, because that's what this graph says, 100 volts, 100 volts. And I've put a dot at the top here because that's the start of the transformer. That is, this waveform here is what you would see if you put your oscilloscope between this point here and this point here. You would see a square wave going into the primary of that transformer. Once again, yes, this is being recorded and you will be able to view it at a later time. We will give you a link for that at the end of the webinar. And oh, yep, this looks extremely complicated because this is the whole inverter bridge for one of our Microfero SE systems. But what I want you to concentrate on, if you take away all this stuff up here, the control boards, the static switch, and everything else, what I want you to concentrate on is this is our battery input here, okay? And here is one set of IGBTs, and here is the other set of IGBTs. And as you can see, there's two in parallel there, and that's all we do to get a higher power rating out of our UPSs. We put IGBTs in parallel to get more power. And as you can see, if we follow, we've got our center tap here, which is connected to the positive, just like all the other ones that we've done before. And we can go through here and we can say, okay, if that's switched on, we go through that transformer back to negative. And then if we have that switched on, it will go through that side of the transformer back to negative. So it is exactly the same bridge that I just discussed that is in our Microfero system, sorry. So hopefully that explains to you how that technology works. So one thing I did want to mention with the strides that have gone on in technology, it allows us now, we never used to, it's a long story, but we used to actually switch analog bridges with SCRs. And now we switch with the IGBTs, we have more control. So we do, rather than just send a square wave out, we can adjust the square wave if necessary. And the reason that we do that is you've got to remember always that we have a battery, okay? And we've got to design our inverter to work at both ends of what the battery is going to see. So at the highest end, on a 60-cell system, is going to be 140 volts. That's the equalized voltage of most lead-acid batteries, okay? So the maximum voltage the battery should see is 140 volts. And then on the lower end, we have 105 volts, okay? And that is the end of discharge voltage that most battery manufacturers recommend. It's actually 1.75 volts per cell. And if you multiply that by 60 cells, it comes out at 105. So our inverter is designed so we can have a range of 105 to 140 volts going into our inverter bridge. But to maintain the power into that ferroresonant transformer, what we can do is we can adjust the trailing edge of the square wave when the IGBT switches off. So I don't want to get too complex here, but a half a cycle or one pulse of a 60 hertz waveform is about 8 milliseconds. I like rounding up numbers, okay? So if the first area here that's at 140 volts, let's say we only need to switch the IGBT on for half of that cycle. So that would be for 4 milliseconds, okay? Then, obviously, if you do the math, 4 times 140, the area under that square wave is 560, okay? And therefore, if the battery just starts discharging and our battery gets down to 105 volts, to get the same power out, we need the same area underneath the curve. Sorry, excuse me. It needs to be 560. So to get that, you would have to divide 560 by 105. And that means the pulse would have to be around about 5.3 milliseconds. So you can see how we can adjust the width of that pulse by when we turn the IGBT off. And that keeps the power going into the primary of the transformer constant between the values of 105 to 140. Okay. Hopefully I haven't blown anybody's brains with going into things a little bit too detailed, but that gives you an idea of exactly how the Microfero bridge works. So now what I want to talk about is our newest technology, the DPP. This is the majority of the UPSs that we sell these days. Okay, DPP is digital process power. So once again, this is an H-bridge arrangement, and we have our battery out here. Everything remains constant. And then we have 4 transistors. Okay, so let's say we're going to turn this transistor on and this transistor on, and they have to be turned on in specific pairs, and you'll see why. Okay, that will allow power to flow down to this point here. Now obviously this IGBT is off, so it cannot go that way, but this IGBT is on, so it can go that way. Ignore this, that's just a choke, but I'm not going to go into that at this moment in time. But that makes this transformer winding more positive than this, because this side here, if you follow down through this IGBT, is connected directly to the negative. So what that does is that gives us our positive pulse again. Okay. And then for the negative side, we do the same with the other transistors. And I've got a better graph to show you what goes on there. So what I just drew there, that's what this one shows. So the transistors that are labeled A, this one here and this one here, are on. That is the power flow. You get a square wave that way. And then if we switch off the A transistors and switch on the B transistors, if you follow it, look, this is positive here, but now, look, amazingly, we follow this down and it goes to the other side of the transformer. So that is now positive. And if you follow this, that's negative, down, back through that transistor B, down to negative there. So that gives us our negative going portion of the waveform. Okay? And in truth, you could, and some UPS manufacturers do for very cheap desk-mounted power UPSs, just go switch on A and then B at 60 hertz, and it creates a square wave, and square waves are usually good enough to power computer power supplies and stuff like that. But that's not what we do. Okay, we get a bit more complex, and we'll go into that in just a moment. And that just shows you on the screen, the red is for the positive half and the blue is for the negative half. Red is going that way there, and blue is going that way there. So, as I said, we don't use a square wave in our DPP technology. We use something that's called PWM, which is pulse width modulation. So first of all, let's discuss what modulation is. In electronics and telecommunications, modulation is the process of varying one or more properties of a periodic waveform called the carrier signal with a modulating signal that typically contains the information that is going to be transmitted. So this is really referencing radio signals, but you'll get an understanding of what's going on. So this is amplitude modulation, or AM radio stations. Okay, so I know it's difficult to get your head around this, but if you look here, if you measure, there's a sine wave there, and you measure the distance between all of these points, it remains uniform the whole way. The frequency of this waveform is not changing whatsoever. Okay, It remains constant. The only thing that's changing is the amplitude. And basically, what this is, it's going to be difficult for me to draw, but this is a sine wave that's at this frequency, whatever that is, which is a carrier wave. But then superimposed on that, what we've added is another sine wave like that. Excuse my poor drawing. And when you add all of these points together, this waveform here is what is created. And then what you'll have on the other end is a signal that removes the carrier frequency, and then you'll be left with just the signal that you sent out. Hopefully you understand that. So that's amplitude modulation, or AM. FM is when we do change the frequency. You can see down at this bottom the output from a frequency modulated system. We're not changing the amplitude at all. The amplitude now remains absolutely constant. But what we're doing here is we are adding the carrier signal, which is not changing frequency. It is a set frequency. And then we're adding our modulation wave, or our signal. And then if you add all of these points together, so you can see here, this is the downward part of the sine wave. So that slows the frequency down here. But as you can get here, this is the higher peak. And what it's doing is it's increasing the frequency. So when you add these two waveforms together, this waveform here is the resulting waveform. So that's frequency modulation. We're adding two waves together and we are creating a frequency modulated signal. So now what we're going to move on to is pulse width modulation. And this waveform here, it shows you that this pulse here starts very, 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 very thin. Okay. And this pulse here is very wide. And then we go out to this pulse here, which is very thin again. Once again, if you measure the time between the midpoints of all of these pulses, the frequency is not changing. And as you can see, the amplitude is not changing. Now all we are doing is changing the width of each pulse. And I'll explain that in just a moment. So instead of switching the bridge on at 60 hertz, saying on for 8 milliseconds, and then these two on for 8 milliseconds, what we're now doing is our carrier signal is 8 kilohertz. So we are now switching these IGBTs on and off at 8,000 times a second. Okay. And within those 8,000 times a second, we are adjusting the pulse width. Now, actually, if you do the math, that works out as about 66 pulses per half wave. So instead of having a square wave, we have 66 pulses per portion of each square wave, if that makes sense. I think the next slide explains it a little more. There we are. Okay. And remember, once again, I said that the DC, the amplitude is not going to change. So if we had a fully charged battery, that's going to be 135 volts DC. And once again, that's going to be 135 volts DC. And all we're doing is adjusting these pulses here. And we can adjust those pulses for load requirements, for, remember we said that the battery could go down to 105? Well, we can change the pulses to accommodate for that. We have much, much more control when you use pulse width modulation. The regulation on our systems with pulse width modulation is much, much better than the ferroresonant technology. The ferroresonant technology is good, just the PWM is better. Okay, and if you did a mathematical calculation of the area under the curve for all of those pulses in this waveform here, basically what you'll get that dotted line. It's similar to a sine wave. I'm not saying it is a sine wave, but it's similar to a sine wave. And then when that gets put into a filter circuit, then we can very easily turn that pulse width modulation wave into a sine wave. So here, once again, let's forget all this stuff down here. We don't need that. That's a control board. You don't need to know how we actually switch the inverter. All you need to know is, once again, on the left-hand side, we have our DC going in, and it's a battery as usual, okay? And then in this circumstance, let's say this is the A transistors, and this is the A transistors, and this is the B transistors, and this is the B transistors. Once again, let's follow the power flow. Now, once again, just like our DSC or our microfero bridge, to get more power out of our system, all we do is we put two IGBTs in parallel. So the power goes down through both of these IGBTs, down here, out here, and out to the bottom of this transformer. I just covered it up, but the start winding is this one here. So that actually gives us our positive half. And then you can see, once again, with A, it goes down to this point here, and then it goes down through both of these IGBTs back to the negative. So that makes that negative. It's exactly the same drawing, just more complicated because we've got gate drive boards and everything on there. So I hope you can see from this drawing, it is exactly the same as the H bridge that I just drew. And just for confirmation, let's make this B. And if only B is switched on, then what happens is, let's go this way here. I always get confused. So that will make that point here. Yeah, so this is negative, so it goes down, and it will go through here to, let me see, my screen is not very good. I should have thought of this before I put it on. Yeah, so this is our B transistors here. So it goes down there, and I always get lost on where this actually comes out. I've cleared it up. So that's B. Let's follow it back this way. Through there. So our negative side is now on this side, and our positive side now goes down to there. So as you can see, we've gone down through here to this center point here, and it comes back up over here. So it makes that positive, and it makes that negative. That's why I don't like showing these drawings with the IGBTs and the gate drive boards, because it does complicate things, because you have all these lines in here. And as you can see, it made it difficult for me to see where the connections were. But that is all we're doing. We're switching positive to negative there, and backwards positive to negative there. But we're doing it at 8 kilohertz now. Okay. And then what we do is we have our transformer here, which is just a regular isolation transformer. It will be, the windings will be designed so whatever our output is here, if this is a 120 volt system, the windings will be designed to give us 120 volts on the output here. And then this capacitor with the inductance in the transformer smooths out that PWM waveform that goes into the primary into a nice, beautiful sine wave on the output that goes out to our loads. So before we go any further, I'm just going to take a drink. So what are the benefits of the DSC inverter bridge, which is the one with the ferroresonant transformer? Well, first of all, it's a much simpler control circuit. the control circuit that tells the IGBTs to switch on and off is very, very simple. It just says, okay, all I want you to do is switch on and off at 60 hertz or 50 hertz, depending what region you're in. And that's it. There's no other complex regulation circuits, such as current limits or anything else like that. The transformer does all of the magic. All we do in our Microfero systems, whether it's a DSE or the old SE, is switch on and off at 60 hertz. Simple as that. Okay. They are robust. The regulation is performed by the Fero CVT, the constant voltage transformer, and it's 80-year-old technology. It's just so reliable. The DSE has excellent fault clearing capability due to the constant voltage transformer. It can supply in excess of 500% of the rated current for a very short time into a short circuit. Okay. The CVT has stored energy, which will supply the fault with the necessary current to clear the fault usually. And also what it allows us to do is, while the transformer is supplying that high current, the IGBTs can be shut down. And remember I said that IGBTs are very, very sensitive to high current. Well, the transformer will supply the current, and therefore we can shut the IGBTs down before they see that high current, and it helps prevent IGBT failure in most cases. And obviously that is our oldest design, so the bridge design is proven, it's reliable, and it's been in operation for many decades now. So they're good, reliable systems, the Microfero systems. So the benefits of a DPP inverter bridge or a PWM bridge. It's modern technology that provides a near perfect sinusoidal waveform that has much, much tighter regulation on the output. So step loads or anything like that, the regulation of our output on a PWM machine is much tighter than with the Microfero systems. It is more efficient. The downside of a ferroresonant transformer is it's a relatively inefficient device. There's a lot of heat generated in its operation. So with just having a normal isolation transformer on the output, we can increase the efficiency of the system. It has a smaller footprint. It doesn't need a CVT, which is usually bigger than a normal isolation transformer, and also the filter circuit is smaller. So it's a smaller footprint. So if space is an issue, then a DPP may be the way to go. It obviously has a wider range of alarm options and monitoring points because it's all electronics. We can do so much more with a PWM system. It also enables greater flexibility for communication, especially via Ethernet, internet, SCADA, DCS. Our DPP systems are much more modern in their design and can communicate very easily with each of those options, and a better dynamic response to load steps, as I mentioned earlier. So both systems really do have their benefits, and I'm not going to tell you which design you should use because I see both have very, very good things going for it. You've just got to look at what your needs are in the plant and figure out which is the best technology for you. So if I am not mistaken, that is the last slide. So I hope that gave you a lot of information. So now what I want to do is open it up to any questions. So if you have any questions whatsoever, please type them into the chat bar on the right-hand side of your screen, and I will do my very best to try and answer them for you. And while we wait for any questions coming in, I just want to reaffirm that this webinar was recorded. You will get a link from Webinar Jam, the platform that you're watching just now, where you can go and rewatch this at any time. Once again, that cannot be paused or rewound. You have to watch it from start to finish. but our marketing department will be converting that into an MP4, and they will be uploading it to the AMETEK solid state control website onto our YouTube channel. And as you can see, Taylor has just put in the chat bar where you can find all of those videos, and you can pause, rewind, fast forward, do whatever you want to do. That will be uploaded by tomorrow sometime. We need to give them time to convert it to an MP4. So we have no questions coming in yet. Either I've melted everybody's brains and they're not working anymore, or everybody understood what I said. Hopefully it's the second one. But I'm going to keep it open until 11 o'clock, just in case you can rack your brains and come up with a question. And please type in the questions. Don't think that it's a silly question. Believe me, I have been asked all the questions in the world. And if you're asking a question, that means you don't know, and therefore I can be here to help you. So here's one that's come in. For a ferro-resonant UPS, I mentioned that the length of the pulse can be modified to ensure constant power. How does that affect the 60 hertz AC output? It does not affect the frequency whatsoever. The switching frequency does not change, because remember I said it's the trailing edge that we can choose when to switch it off. The leading edge always turns on in a 60 hertz pattern, so the frequency will never ever change. Okay, so hopefully that answers your question, Eric. Taylor's also put in the chat bar there that if you need any assistance whatsoever, you can go to our website and you can click on that link to get to the contact us form page, or you can contact us using the email address sci.marketing@ametek.com, and they will route the email to the appropriate person. And you can also call our 1-800 number, 1-800-635-7300. That will take you to our main switchboard at the Columbus factory in Ohio, and your call will be routed as necessary after that. So once again, I'll keep it open for any more questions. What I would like to ask is, we always send out a survey at the end of every webinar. And I'm not looking for 5-star reviews or anything like that. What I want out of the survey, I think it's one of the last questions in the survey, is what would you like the next webinar to discuss? And I do read every single one of those, because that's what drives next month's webinar. I look at all of those answers, and then I can say, okay, everybody wants to learn about a static switch or today's inverter. So if you could fill out that survey and let me know what you would like us to discuss on the next webinar, that would be truly appreciated. And obviously, if you want to leave a 5-star review while you're doing it, I'm not going to complain. We've got another question. Are these inverter designs universal or proprietary to AMETEK? It's a very good question. They are pretty much universal, especially for the PWM machines. All PWM machines, whichever manufacturer it is, they use H-bridge technology. So it's pretty much universal. The Microfero design that we have, it's a bit more proprietary. There are very few manufacturers out there in the industrial world these days that are making ferro-resonant CVT UPSs like we do. So that is kind of more proprietary. But on the DPP side, most manufacturers use the same bridge design. Question about regulation. Could you approximate regulation for 100 kVA? Ooh, I can't do that Mohsen off the top of my head, but what I can do is I always print out a report of all the questions at the end of the webinar. I will pass that on to the correct person, because I don't think I've got a DPP brochure on my desk. Let me look. No, I cleaned my desk off last week and I don't have one. I will have to get back to you on that. But I'm pretty No, I'm not going to stay. I think for the CVT systems, for the ferro-resonance systems, it's 5%, and is it 2% for the DPP? I can't remember. I will get back to you on that. Okay. So you've got a few more minutes to ask any more questions. And don't forget, actually, I'm coming from our service and training center in Stafford, Texas, and our training center is back open, and we have full classes going on now. So you can go on the AMETEK Solid State Control website, and there is a calendar there for when our next training classes. We do separate the classes. We have our DPP training class, and then we separate it with our SE, DSE, Microfero training classes. So if you are interested in coming to Houston and getting some absolutely fantastic training, it's a 5-day class. We do some amazing battery training for the first 2 days, and then we do a lot of hands-on stuff. We have a full lab in our Stafford facility that has every UPS that we manufacture, and we put faults in them. We get you to troubleshoot it. It's honestly, everybody that comes here says it's one of the best training classes they've been to. So if you can persuade your supervisors, or if you're an engineer and you want to come and learn more about our UPS systems, please go to the website, give us a call. You won't regret coming to our classes. They really are fantastic. And they happen on average once a month. And you can also, if you can't spare technicians from your plant to come to us, we can come to you. We can ship out one of our training UPSs to your site if you have a training room, and we will do the training at your site and get all of the plant electricians and engineers trained in one go. So we do supply all of those services. And Taylor's also put a link into the classes there. So I think that's really about it. We've got no more questions. So as always, I really, truly appreciate you taking time out of your day to watch this presentation. I know that your day is filled with a lot of stuff and you are very busy people. So you taking time out of your day really makes me smile. It's very appreciated. And if you have any other questions or concerns, please don't hesitate to give us a call or email us. We will do whatever we can to give you the information that you need. So until next month, we will send an email out a week before the webinar as usual, letting you know what it's going to be about. Take care. Have a very safe Wednesday, Thursday, and Friday. Enjoy your weekend and take care until we speak next time. Thanks again, and we'll see you soon.